Okay, so before we move on, were there any questions on the announcements? So we've got a quiz next time, right? What should you bring to a quiz? Calculator. No, I don't think that we can, because the focus on the quiz is going to be the homework you just turned in. And so if we postpone it, then maybe some students are forgetting things. I like to strike while the iron is hot, as they say. Yeah, so we'll have it on Tuesday. Yeah. The quiz includes everything including today's lecture. But it'll emphasize mostly the assignment that you just turned in. Okay, any other questions before we move on? I haven't written it yet, so I don't want to make any promises about what it'll be. I want to have a, yeah. What it's not going to be on the quiz? The quiz, well, we're not going to have philosophy on the quiz. Harry Potter won't be on the quiz. No. Everything that was covered in quiz 1 won't be on. So if you look back through the list of the course schedule, the topics that are on the course schedule after quiz 1, including through today, will be on the quiz. Yeah. No. I could, but for the same reason that I don't post the, because I plan to use these questions again next semester. So you can stop by my office if you want to check on it. All right. Waterborne disease. That's why, environmental engineering is said to have saved more lives over the years than doctors, because environmental engineering is responsible for preventing so many diseases. And we're going to look at some of those diseases. But first, take a look at this chart. This is showing back in the United States the effect of water treatment on typhoid. And during the 1800s, when cities were starting to get larger and larger, they hadn't yet perfected how to maintain good sanitation in cities. They weren't disposing of their wastewater in an efficient way. And as a result, the drinking water was getting contaminated by the wastewater. And so you can see typhoid is a very bad disease. It's, in many cases, deadly. And there was hundreds of typhoid cases per 100,000 of population. So, where it says 300, that means 300 cases of typhoid for every 100,000 people in a city. So a million-person city would have 3,000 cases per year. So there were these spikes of lots of disease, and then you can see in 1906 they started to filter the water. And instantly the disease rate went down quite a bit. Not to zero, but it had an immediate impact, this idea of filtering water. And then what dropped it down even more was chlorination. And that's using chlorine to disinfect and to kill any of the bacteria or viruses that remain in the water after treatment. So you can see an immediate effect. Now, unfortunately, there's a lot of places in the world that don't have effective drinking water treatment. And in fact, still today, even now, in our age of technology, more than 1.8 million deaths each year are attributable to waterborne disease. And so if you stop and think about what makes it in the newspaper, if an airplane crashes, that's all across the front page. And several hundred people die in an airplane crash, which is very tragic. But more tragic is 1.8 million deaths every year when it's so easily prevented. In the next several lectures, we're going to go through drinking water treatment, and you're going to see it's not a mysterious process. It's something that's very easy to do as long as you have access to just the most rudimentary technology and a little bit of know-how. Some of the diseases, this is like a list of waterborne diseases that's all together in one place, I noticed from Wikipedia. You'll probably recognize many of these diseases, like amoeba is a pretty famous one. In the United States, Giardia is a big disease that people get when they go camping in the mountains. They drink water from streams, and then they can get Giardia. back in the 1990s, there was a city in the United States that had cryptosporidium, which is it is like a spore, and it got 500,000 people sick in the United States. Some of these other diseases are more commonly heard of with respect to like big outbreaks in war zones or in developing countries, like cholera, dysentery, E. coli. But then there's some that are continuing to plague even developing countries, like Legionnaire's disease. There's a lot of news lately that the United States is having an outbreak of Legionnaire's disease. So typhoid fever, Vibrio, there's a lot of things you can get from drinking water that's not pure. So we'll begin by talking about some of the physical characteristics of water. Now, in the picture, you can see two rivers coming together. And we saw a similar picture when we were looking at Pittsburgh and river mixing. But why I like this picture is that it's showing the picture on the right, well, the stream on the right has a lot of turbidity. Turbidity just means suspended particles that interfere with the passage of light. So off on the side you can put turbidity is suspended particles. Then they may be harmless particles. Like what we're seeing here is clay. It's soil. And soil by itself won't make you sick. But what can make you sick is if there's germs inside of the soil, and then the germs get into your body and they're protected by the soil. Even if you're chlorinating water that has a lot of turbidity, the germs can sort of hide from the chlorine inside of the turbidity. And so turbidity is one of the things that has to be removed through the water treatment process. Some of the other things here are not so critical. Like, it's not fun to drink water that has a yellow tint or a brown tint to it. You look at it and it's unappealing, but that's an aesthetic issue. The color itself won't make you sick, and sometimes is harmless. If you think about food coloring, you know, that's changing the color of a cake frosting, blue or red, color itself isn't a problem, but sometimes it can indicate a problem. And the same thing is true of taste and odor. Does anybody here ever drink water from the tap here in the UAE? I do, sometimes. In the middle of the night, I don't want to walk all the way downstairs to use the water cooler. I'll just drink from the sink. And there's nothing wrong with the drinking water here. It's perfectly safe. But it just has a flavor that's not, you know, to our liking. And it's also a little bit due to the temperature. Like drinking warm water doesn't have a very good flavor, right? I see lots of faces like, ooh. What do you mean? No, the tap water's fine, I'm telling you. If you have a tank on your roof, that can be a concern because bacteria can grow in those rooftop tanks. But if your water's coming straight from the drinking water network, that what the CVE puts into the pipes is safe to drink. The tanks on the roof of a high-rise? Yeah. The tanks you have to be careful about because if they're not properly maintained, then bacteria can grow in them. Right. I don't have a filter and I also don't have a tank, so maybe I'm safe. I don't get sick and I never have. I drank that water when I was here previously for 4 years and I never got ill. Maybe, yeah. All right. So it shows that we avoid water sometimes because the taste is not what we like. Why is the taste a little bit off here? Where does our drinking water come from? Yeah, it's desalinated water, and they add a little bit of minerals. If they didn't add any minerals, then it would cause corrosion in the pipes. So they have to add a little bit of calcium carbonate and other minerals just to prevent corrosion. But there's also a little bit more sodium and chloride than we prefer to have for the flavor. Chemical characteristics that interact with water treatment and what we do. Some of the chemicals that are important in drinking water include chloride. Chloride and sodium because of flavor issues. But fluoride, does anybody know what's significant about fluoride in drinking water? Hopefully the drinking water that you used as a child was fluoridated because it strengthens the teeth. Having a little bit of fluoride in your drinking water as you're growing, it's less important for adults, but for children, in places where they have fluoride in the drinking water, the teeth and the percentage of dental caries, like cavities, is much, much lower. If there's too much fluoride, it can cause mottling of the teeth, and that's what this is. I'm sorry for the disgusting close-up of someone's mottled teeth, but we'll see plenty of disgusting pictures through the semester. This is environmental engineering, all right? But yeah, so this is because they had too much fluoride. So there's a range, an acceptable range. Usually what we like in drinking water is between 0.4 milligrams per liter and at max 1 milligram per liter. Does anyone know why it would be bad to have lead in the water? Why? Exactly. Yeah, there are neurological effects to having lead in the water. And the problem with that is that for many years, pipes were made out of lead. They say that lead piping maybe contributed to the fall of the Roman Empire. You know, people have speculated about that. That's right. Yeah, they did. They added it to wine to try and make the wine seem better, which it's a bad thing. All right, iron and manganese. Those things don't cause health problems, but they do cause staining, because both iron and manganese have ion states that are oxidizable, so they can stain clothing. And if you saw this, you'd think maybe that the water is contaminated and poisonous, but it's not. It's totally fine. It's just that the iron precipitates, and once it precipitates, it looks like rust. And so that's iron that's been oxidized. So sometimes when we go through water treatment, we have to make adjustments to the chemistry of the water. And the steps that we're going to be covering over the next couple of days will talk about those adjustments that have to be made. And then these are the ones that really cause the most health issues. If you look worldwide, what's happening? People get ill mostly because of microbial contamination of their water. And the categories of microbial contamination include viruses, and this is a picture of the flu virus, influenza, bacteria, and this is a scanning electron microscope photo of E. coli, which is used as an indicator organism for contamination of drinking water. Protozoa. This is a close-up of Giardia, which is just a spore-forming organism that can get in contaminated water and cause a lot of illness. And then helminths, which is a fancy word for worms. Worms can get in the drinking water too. Some of these are really easy to remove and kill, and some pathogens are very tough, and we have to be a little bit crafty to get rid of them. Protozoans are usually considered pretty tough. They're hard to kill. Yeah. Spores can survive in water, and it's amazing how hardy some of these things are. A spore sometimes can get dried out and rehydrate it, and it's fine. It's as though nothing ever happened. Some of these are really rugged microbes. So as an overview, we're going to step through, basically I'm going to take you on a virtual tour of two different kinds of water treatment plant. And the treatment plant is designed to adjust all three of these categories to make the water safe and palatable for humans to drink. And by palatable, I mean good for the taste, that it's aesthetically pleasing. So we don't just stop at safe drinking water, but we also want to make the water pleasant for people to drink. So we are going to try and remove the things that are undesirable. There's a couple of different types of treatment plants depending on where you get the water from. And in fact, I should expand this list to include, there's flash desalination, there's reverse osmosis desalination. There's so many different kinds of desalination technologies. Those are usually considered in more advanced treatment classes. The more typical type of drinking water treatment is what we're going to be covering in this class, but we will have some lectures that are devoted to desalination focus. So here I've emphasized the word ground. Groundwater is what comes from a well. Does anyone know how much of the drinking water, how much of the water we have in the UAE is from groundwater? It's less than 10%. More than 90% of our water is desalinated, and then usually the groundwater is what goes into the bottles. You know, like if you order Masafi or Al Zulal, those big 5-gallon bottles that you get delivered to your house, those are typically groundwater. And some groundwaters have to be having their chemistry adjusted. And so what usually happens during a groundwater treatment plant is that the water comes in and is mixed with chemicals in the rapid mix, and in the reaction basin, a precipitation reaction will occur. If you're trying to remove excess calcium, or if you're trying to remove excess iron, for example, that removal happens in the reaction basin, and then it's settled, and what you remove off the bottom, the precipitate, is called sludge. The water that comes off the top of the settling tank is recarbonated to make the mineral balance desirable. It's filtered to remove any pathogens that might be present, disinfected to kill any pathogens that made it through the sand filter, and then stored and transmitted to people through a distribution network. Some plants don't do all of these steps, though. Sometimes the drinking water, if the minerals that the water is in contact with underground are favorable for it, sometimes all they'll do before putting it right into the pipe network is they'll take it straight from the well and chlorinate it. In other places where they fluoridate the water, they'll add fluoride, they'll chlorinate, and then put it directly into the pump. So let me show you a couple of pictures. This is the drinking water that serves Purdue University, which is where I got my PhD. And some of my research was having to do with the wells that were on campus. And so you wouldn't know that there's a well here other than there's a building that's housing several pumps. These fire hoses aren't usually there. Those fire hoses are there because they were doing maintenance and flushing out the pumps while I was doing my research. So when you go inside that pump house, you can see here's a big pump, and the electric motor sits at the surface, and then there's a metal shaft that goes down underground, and it's spinning. And as it spins, underneath is the pump, which lifts the water back up to the surface. And at this well, I think that the water was about 80 feet underground. So we're talking maybe in the range of 25 meters underground to the water table here. It goes up through a series of valves, and they can control whether or not this pump is entering the network by this valve. They can just close it off if they need to. Here's a look at a different treatment plant. This is in Indianapolis, in Indiana. And in this treatment plant, they were doing something a little bit different. They couldn't put the water directly into the pipe network because they had so much iron there. So they had to pump the water up to the roof of the building, and then they were spraying it through a collector just to try and get the iron to oxidize. If you have iron touch air, that's when it can start to rust. You know, a car that gets a lot of water on it can start to rust over time. Luckily, we don't have that problem here. Cars don't seem to rust because there's not that much rain. But here, they pumped the water to the roof and then sprayed it down through these filters that encouraged the iron to precipitate. Here's a look at where the water is being chlorinated. And so they were pumping in a chlorine solution through that valve, and it's just mixed inside of the pipe as the water is flowing downstream. Anyone guess what this staining is from? Iron. Yeah. This is iron. And so once the water goes into here, the iron is ready to come out. And underneath the water line is some sand. And the water is flowing downwards through the sand, and those iron particles will stick to the sand. And as they stick to the sand, then the pure water travels down through the bottom. Just another view of that sand filter. Once the water is collected from underneath the sand filter, it was going to this is injecting some more chemicals. And so I think that this is where the fluoride was going in. And it was using a programmable module that, based on the flow rate, they're measuring the flow rate as it goes through the pipes. It knows how much of the chemical to inject as well. So that was groundwater. And we do have groundwater treatment in the UAE. Less common in the Middle East is surface water treatment. There are some places where they have surface water treatment. In Iran and Iraq, they've got surface water treatment. I don't think in the UAE we have any surface water sources that we use for drinking. There are some that are used for irrigation. But the difference here is that the water chemistry is different. You know, water that comes from underground was just in contact with minerals. Water that's at the surface is in contact with lots of pollutants that exist at the surface. Animals are living at the surface. People are at the surface. We're driving around our cars, discharging waste from factories. And so surface water, like that's coming from a lake or a river, it has all of those things that you'd expect at the surface. And so we have to change some of the treatment steps. Some are the same. We still have mixing of chemicals, for example, and there's still a basin where a reaction is occurring. Here it's called a flocculation basin, and we'll talk all about that. Sedimentation is like a settling where particles have time to just settle to the bottom and the sludge is removed. There's still a sand filter to try and trap even smaller particles that couldn't settle naturally. Adding a disinfectant is important, storage and distribution. So here's a look at a river in Indianapolis that water is coming into a treatment plant from. You can see it looks brown. And that's because this watershed has a lot of upstream area, and when it rains, the soil is washed downstream. There's a lot of silt and clay that gets suspended in the water here. And so what they do is they have an intake taking water from the river into the treatment plant. This is when I went back one day. I was doing my research at this intake, and I couldn't get out to the building because the water level in the river was so high. They were having flooding there for several weeks. So I thought about swimming out to there, but it was in the middle of winter, so I didn't do it. I didn't swim out there. Here's some more pictures of the treatment plant. So the water that comes in is mixed with a coagulant. It's a chemical that tries to make the clay particles stick together. Because when the clay particles stick together, they settle more easily. And so this, what we're looking at in this picture, is a settling basin. The water here is very calm and smooth so that the particles can settle to the bottom and the clean water can flow over the top. Here is a clarifier where this underneath the water line is an arm that's rotating around that kind of scoops the sludge into a vacuum, and the sludge is vacuumed away to be dewatered. Here's a close-up of the water. And remember how brown the river was? The water now has a better clarity. It hasn't gone through a sand filter yet, but it has an improved clarity. Now, you're thinking, oh, this looks really dirty. How can that be healthy for this water to be in contact with what we're going to drink? This algae actually, it doesn't cause any harm. It grows. There's sunlight, there's water, there's nutrients in the water, and so something's going to grow. And it's an aquatic plant that grows. And they still are going to disinfect this water, so whatever pathogens are there will be removed. This picture shows breaking up surface water treatment into things that are strictly chemical treatment, chemical and a physical process, those that are only a physical treatment process, and those which have a biological component, which is chlorination to try and kill any pathogens that are left over. Surface water, as we talked about, the more contact with humans, that makes it worse quality than groundwater. You can drink directly from a well, and in most cases you won't get sick, unless the well is under the influence of things from the surface. For example, if there is a latrine too close to a well, then the pathogens from the latrine can contaminate the well. But in most cases, we try and keep those things separate so that the well water quality is preserved. But surface water has constituents coming from factories, which use the water for cooling, or they discharge their wastes to the stream. And there can be a lot of changes over the seasons because farmers apply pesticide usually in the spring and summer. And so during the spring and summer, we have to be on the lookout for those sorts of pesticides in the surface water. But then in the fall and in the winter time, it's a lot less common to see some of the pesticides and extra fertilizers added. Here's a picture of an arid environment where during the summer we don't see any water, but during flash floods you can tell there's evidence of a stream that's formed there. And so there's a huge variation seasonally that comes about from drought conditions. Now, we are going to have each of these topics over the coming lectures, and I wanted to point out how they feed into the next homework assignments you have. we're going to have rapid mix and softening go into homework 5. And if you look in the book, some of these are a little bit, the order that we're going to take it is slightly different from the order in the book. Just for simplicity, those two are joined together. We're going to talk about coagulation, flocculation, that leads into homework 6, and then filtration and disinfection for homework 7. All right, so that's all the time we have for today. Let's just take one final look at the announcements for today. We are going to have a quiz next time. We'll take about 10 minutes for that quiz, and then it'll just be a regular class after that. I will see you then, and I hope you have a good day.